with probability theory. Normally works on probability theory with an emphasis on discrete spatial models, but I couldn't resist to say that he's going to talk about a very different discrete spatial model today in looking at Lego and how to do Lego construction for mathematical artists and artistic mathematicians. So happy to introduce Alexander.
All right, thank you very much. Very exciting to be able to give this presentation. But hopefully you can see this. Yes, so, well, I want to focus on a particular medium for mathematical illustration, potentially. And as is clear from this sort of slightly confused title, I don't really know what I'm doing with this medium. Am I using it to illustrate mathematics, or am I just trying to produce art inspired by mathematics? I really don't know. I just do things that I find fun and interesting. So it is what it is. So yeah, so what are we, and by the way, I've never given a talk like this before, so I have no idea how it will go. I will do my best. So what are we actually talking about? So the Lego company, I guess everyone's heard of it, right? Probably the biggest, most successful toy company in the world. So they actually started off in, I think, the 1930s, not producing the familiar plastic blocks, but producing wooden toys. It was a family-owned company, and it still is, interestingly. It's not publicly traded. And then in about the 1950s, they came up with this sort of key patent for the familiar interlocking blocks. And interestingly, they were not the first to come up with that general idea, but they really perfected the idea and made it much better, made it work much better. And so, progressively over the decades, they produced more and more sophisticated things like this set, for example. And then what I particularly want to focus on is something which the Lego company calls the Technic theme, which is, well, a sort of sub-genre of mechanisms, a system that can produce working mechanisms. And this sort of started off in the 1970s with the basic idea being you have your basic Lego bricks, but some of them have holes in, and then there can be axles or pins in the holes, and axles can rotate, and they can have wheels or maybe gears on them. And so again, it became more and more sophisticated over the years. Then kind of an interesting thing happened in the 1990s, as illustrated by these two pictures here, 94 and 99. They changed to a sort of a different system where there are no longer any studs. So before that, it was really, the pieces sort of looked like Lego bricks, but not like the traditional Lego bricks that everyone recognizes, but they have holes in them. But they still have the studs on top, and then they decided to get rid of the studs, and this produces far more realistic looking models like this one. So of course they were in part responding to what they perceived the market wanted, but interestingly, it's still compatible. So every Lego piece that's made from 1950 to 2023, they're all compatible with each other. It's a wonderful thing. So in particular, this sort of studless design theme is fully compatible with the old standard one. And again, things became more and more complicated and sophisticated until you have incredibly complicated models like this one. So all these are official sets that you could buy at those particular times. Briefly mention some competitors. So, you know, there are other systems of well, toys that enable the construction of complicated mechanical devices. So, for example, Meccano, well, I guess Meccano in Europe, Erector Set in North America, it's called, is one of them. And you know, so they all have their strengths and weaknesses, I would say. Some are better for some things. Personally, I'm a big fan of Lego, as you probably work out. And then I should also mention there are, particularly these days, there are a number of clone brands, which if you look at the pieces, they look virtually indistinguishable from Lego, but they're not made by Lego, they're made by other brands who copy their ideas, and there's sort of a range of, I think some of them do it legitimately, and they make sure they're covered in terms of intellectual property, and other companies not so much, actually. So it's a complicated subject that I'm not going to get into, but as you can imagine, hardcore Lego fans like me don't really approve of the clones. And I mean, one of the things that makes this such a fun medium to work with is that, you know, although it's absolutely designed and sold as a children's toy, there's a very significant adult Lego fan community. And for instance, we have big shows where people show off their creations. So this is an image from VidCon in Seattle, a very big show. And another interesting thing is there's a very significant ecosystem of well, third-party marketplaces for Lego parts. I'll talk a bit more about that later. And also software for digital building, so CAD specifically for Lego. And you know, most of that's just written and maintained by enthusiasts. And before I say too much more, I should point out that the Lego company is very protective of their trademarks and their intellectual property for very good reasons, I think. So I'm required to inform you that Lego is a trademark of the Lego group of companies, which does not sponsor, authorize, or endorse anything that I'm saying. And Lego are also sort of particular about how their trademark is used. So they insist that it's an adjective, not a noun. So you can talk about Lego bricks, but you don't want Lego to be used as a noun, and especially never put an S on the end. Lego is not a good thing to say. It marks you out as someone who doesn't know what they're talking about. Anyway, right, so with all that out of the way, let's actually talk about some interesting stuff. I've sort of tried to divide this talk a little bit into different areas to try and make it something other than just showing you a bunch of fun things, even though that's really what it's going to be. So first of all, let's talk about static structures. So let me stop sharing and try to show you some actual things on video. I hope this works. I'll just see. Right. So Right, so here are some bits of Lego. So this is what I was talking about. This is the studded style, and this is the studless style. So we have these beams of various lengths with holes in them, and pegs that you can connect them with. So, for example, suppose you're interested in triangles. Well, you could make an equilateral triangle like this. So this is just 3 equal lengths, and of course we have a equilateral triangle with angles of 60 degrees. One thing you might not know if you haven't thought about it, are there any other triangles with integer sides that have an angle of 60 degrees other than an equilateral triangle? And it turns out there are. So here is one. That is a 578 triangle that I've just made, and it has an angle of 60 degrees here, same as the equilateral triangle. So, the point I'm trying to make with this is not that this is a particularly interesting piece of mathematics, of course, but it's just an incredibly convenient medium for playing around and experimenting with stuff like this. It takes 2 minutes to knock together something like this. Let me show you something else. Here's maybe how you might discover some mathematics. Here is to show you a way that you might discover Pythagoras theorem from scratch. So here is just a square grid of holes. And actually, I've got 2 pieces like that. So I've got a square grid of holes on one side and a square grid on the other side. And I've fixed them together with a little pin in the middle so they can rotate. Okay, so everyone see what's happening, I hope. So you might ask yourself, hope you can see this. If I rotate them, you see the sort of pattern of the holes changing. Are there any angles I could put this top one at, so that other than 0 degrees and 90 degrees, of course, are there any other angles I could put it so that some of the holes would line up exactly? Right? You might ponder this. We're just playing about with the parts. And actually, of course, there must be, right? Because I could go a knight's move from this starting point where they're connected together to there. So I've gone 2 places along and 1 place up. And then I could make that line up with a knight's move the other way underneath. And I think that's like that. Right? And the holes must line up, right? Because I've gone on the top, I've gone along 2 and up 1, and on the back it's a bit harder to see, but it's the other way around. It's along 1 and 2 in the other direction. So they must line up, right? And it's already an interesting angle. And then are there any other holes that line up? Well, yeah, there must be, right? Because let's see. So well, there's one there. It's really hard to hold it in the right place. There's one there because that's just another knight's move here, so that corresponds to another knight's move on the back. And then actually maybe I should do that one first. Right, so that's another knight's move in the same direction. So that lines up as well. And then if I go 90 degrees from that, a knight's move that way, well, that also must be a knight's move downstairs. So that's also a hole that lines up. And then actually I've done something interesting though, because I've ended up back on the same row that I started with, as I've done these 3 knight's moves. So it's up 1, and down 2. But what have I done on the back? I've done something genuinely different. So I've gone along by 3 and along by 4. So I've just proved that a 3, 4, 5 triangle is a right angled triangle. Right? I've just proved that instance of Pythagoras theorem. But actually, if you think about it, you can prove the general Pythagoras theorem like this by the same sort of construction. And then there are other things you might consider as well, right? So if you are there any other ways I could make it line up? I won't try to do it, but well, potentially yes, because like 5 squared plus 5 squared is 50, and that's also equal to 7 squared plus 1 squared, right? So I could go 5 and 5 on the top, and then 7 and 1 on the bottom, and that would line up. And then if you do that, you find actually that's the same as one of these type of arrangements, so you don't get anything new. So anyway, none of this is hard mathematics, of course, but you can see there's a whole investigation that you could do starting from here. And again, just start with 5 pieces of Lego and you discover it for yourself. So what else did I want to talk about? Yeah, so some more. I mean, here's a just slightly more interesting piece of static geometry. So this is a regular nonagon, 9 sides, and this is a rigid bracing of it, just using unit length struts. All the struts are the same length. So yeah, so the things you can construct using rigid bracing are strictly more than the things you can construct using ruler and compass. So you can get regular nonagon, for instance. What else did I want to talk about? Yeah, here's, before I go back to my slides, here's something else. So this is a knot. It's a trefoil knot, in fact, and it's embedded in, well, if I hold it like that, everything lines up in a Y shape. So it's embedded in a Y cross a line, Cartesian product of a Y and a line. So if you like, it's a book with just 3 pages, and you can embed a knot in it. So you know, this came up from a little discussion on the Illustrating Math Discord group, and you know, some of us realized you could do this, and in fact it's been known for a while. There's papers all about this, but again, this Lego just provides a really, really convenient way to just make this thing, which is quite hard to visualize. Of course, if you're good with 3D printing, you could 3D print it. But for me, you know, I was able to just make this in 15 minutes. So this is part of my point. Now let me go back to slideshow. It's a long time. There we go. So here's another static sculpture. This is something that a lot of people will recognize. This is the latest miracle from Smith, Myers, Kaplan, and Goodman Strauss. This is an aperiodic monotile that doesn't require reflections. And this is a Lego version of it, produced by this gentleman, Michael Verschave. I'm not sure how you pronounce it. And this is actually a digital build. So this is produced using CAD software, but you could make it in real life. And I think he's made a few of them. It would be very expensive to make a piece as big as this thing. That's the knot that I told you about. So what about sculptures in 3 dimensions? So here is a very nice design by a gentleman called Rocky Lau. It's a compound of I guess it's 6 pentagons arranged in a very beautiful symmetrical arrangement. And this actually, each pentagon is just 5 separate pieces, and they're just held together by tension. It's very beautiful. And here is something that I came up with, and probably I didn't. Probably someone else has come up with the concept before, but this is it's kind of hard to see in the picture, but it's a repeating 3-dimensional lattice, which is composed of 3 sets of helices, or each set is parallel helices, and they somehow wrap around each other in this interesting way. And this is a diamond lattice. This is the crystal structure of diamond, and not sure if you could tell, but this is very big. This is about 1.5 meters high. A very long time to put it all together. That's by me. All right, so let me now move on to something a bit more sophisticated in a way. Let's talk about linkages, things that actually move. And again, let me my table. So yeah, so again, it's just super easy to experiment with things. So say you're interested in 4-bar linkages, which of course are a very very famous topic, lots of interesting mathematics there. If you want to make a 4-bar linkage, well, you know, here it is. This is just literally 8 pieces, and if I get bored with that linkage and I want to experiment with a different one, I can just move to a different hole, and here's a different 4-bar linkage. A really long time ago, which I've been sharing and not for some reason. So here is a video. So loads of interesting videos on YouTube of Lego mechanisms. This is by, well, this is a channel called AK Lego, and now you see what's happening. There's a 4-bar linkage driven by a motor, and this point traces an interesting curve. I believe it's a lemon skate. And here's a very, very sophisticated model, and this is sort of a different direction. This is if you want to, I guess this is very much more in the direction of art informed by mathematics rather than the other way around. So this is a model by Jason Alleman, and well, hopefully it speaks for itself. Remarkable motion. Right, so this is kind of the point I want to make. So Lego pieces as a medium, it's super easy to just experiment with things. If you find yourself wondering about almost any question involving mechanisms, you can try something in 5 minutes. And on the other hand, if you really want to take it seriously, it's possible, definitely much harder, to produce very, very sophisticated and beautiful constructions like this one. And here is something else. This is my video, although again, I'm not the first person to find this. This is a three-dimensional linkage. So if you take 6 cubes and you join them together face to face, kind of in a loop, then a couple of ways to do that, but there's sort of, this is the most interesting one. If they're joined in this sort of chair formation, then you get a three-dimensional linkage with exactly 1 degree of freedom. And it's a loop in the configuration space as well, so you can keep on going around. And that's yet another intriguing linkage. This is on the YouTube channel of somebody called, or someone whose channel is called Diamabolo. Very interesting person. There's all sorts of amazing mathematical type stuff on his channel. And this is also mine, and again, it's not my invention. This is somehow well known as a concept. How to describe it? You have this. You have a hexagon with these 3 slots running through the center of it, and you can have 3 rotating points arranged in an equilateral triangle, each one of them sliding in one of the slots, and that results in, if the equilateral triangle rotates at a constant speed, then the hexagon also rotates at exactly half the speed. Okay, so now let me tell you about something sort of genuinely new. And again, I'll stop sharing. So, okay, so here's an interesting and known piece of mathematics. If you have suppose I have an object, like my calculator here, 3-dimensional object, and it's tethered to the ground somehow. Maybe it's tethered by a piece of string or a chain, or in this case by my arm. Is it possible for the object to rotate continuously about an axis, rotate round and round and round, without the tether, in this case my arm, getting twisted up? Actually, rather surprisingly, the answer is yes. So if I rotate, I have to do it the right direction, right? So now I've rotated it through 360 degrees, and you can see my arm is all twisted up in a very uncomfortable way, but I can actually keep going, rotating it the same way. And if you're more athletic than me, you can have it just perfectly rotating about an axis. And now after 2 turns, it's back where I started, right? So this is a known phenomenon. So it's mathematically, it's intimately connected with the double cover from the group of unit quaternions to the group of rotations that fix a point, 3-dimensional rotations. And also it appears in various traditional dances. There's something called the candle dance, and there's something called the plate trick, where basically people do this with for instance, a lighted candle or a bowl containing liquid or something like that. So I became interested in the question of, could you, I mean, this is a really hard motion to understand, right? Even if you see someone doing it with their arm, it's kind of hard to understand quite what's going on and why it works. So I began to wonder, is it possible to make a mechanical linkage that would do this, that would do essentially what my arm does? And ideally, it would be just purely mechanical. I mean, of course, you could do this if you had a robot arm that just literally simulated my arm with about 10 motors in it, all controlled by a computer. You could obviously do that. But I wondered whether you could do it just mechanically. So really, you just turn a handle and some kind of robot arm does what my arm just did. I eventually managed to do this. The idea for how to do it came from, so first of all, this is a universal joint. So this is a thing that you find in vehicles and all sorts of other machinery. So it enables you to transmit rotation motion through an angle. So I have a shaft here and another shaft here, and they can be at an angle, and they can transmit rotation from one to the other. To hold it at the right angle here. There we go. Here's a bigger version of how the mechanism works. So it's a very common, well-known mechanism. It basically has these two yokes and then a sort of solid blob in the middle, which is pivoted to both of them. And one thing I noticed is here's another version of the same mechanism. So it's mechanically exactly the same, except that the blob in the middle is a ring on the outside instead. And this is interesting because it enables you to, if I can get this, it enables you to put a something solid in the inside. And so here, for example, properly, but here I have a solid bar with an angle in it in the middle, and then this thing just rotates around the outside of it. So it's really it's equivalent to a universal joint, but somehow arranged differently in space. And well, based on that, let me go back to the slides again. Based on that, I managed to come up with a device that does the plate trick, a mechanical device. So here's what it looks like. It's a whole sequence of these inside-out universal joints with a solid piece running through the middle that has this sort of question mark shape. And let me try to show you it in action. Hi, I'm not going to do the sound. So here it is. So there's a little cube on the end, and when I turn the handle, the cube rotates continuously in the same direction. And as you can see, there's a piece of string running along the outside, tied to the frame and tied to the cube. And no matter how much I rotate, it never gets tangled up. So this, so this is doing the equivalent of what I was trying to do with my arm. And yeah, so certainly to me, at least, just really thinking about this and understanding what was going on and playing with the model genuinely helped me to understand this mysterious physical phenomenon. Hi, I'm Alexander. So by the way, how much longer should I go on? Should I go on until the hour, or do we stop a little bit before?
It looks like another 10 minutes.
Okay, yeah, perfect. Right. Okay, so let's talk about gears. Everyone loves gears, right? So of course, Lego comes with a whole bunch of gears. And again, let's look at some. So for example, here are 2 gears, little one there and a big one there. And I'm sure most people know the way gear ratios work is you look at the ratio of the number of teeth. So this is a 1:5 ratio. I have 5 times as many teeth on the big gear than the small gear. So if I turn in this direction, it's a 1:5 ratio. If I turn the other one, it's a 5:1 ratio. So I produce the output is going 5 times the speed, but with 1/5 of the torque in my input. Here's something else, even more interesting though. This is a differential gear, this mechanism right in the middle. So this is again commonly found in vehicles, and it enables a powered axle to go around a corner. So when you drive your car around a corner, both wheels are being powered, the one on the left and the one on the right of the drive axle, and they have to go at different speeds to go around the corner, right? And they're both being driven. That's done by a differential, and Lego, of course, makes one. This is what it looks like. You have 3 little gears in the middle, and then you have this outer shell. But we can also use it to do arithmetic. So there are these 2 side shafts, this one and this one, and then I can connect something to the outer shell of the differential like this. And actually what it does is the speed of the outer shell is always the average of the 2 speeds of the side shafts. So for instance, if I hold that side shaft stationary and I turn this, and that's turning at half the speed, in fact, and I can do the same the other way around. So this enables us to do various interesting things. Let me show you some examples. Right, so as I said, so here's a differential. You have 2 side shafts. The speed of the central shell is exactly the average of the 2 speeds. So here is a remarkable thing that somebody did. Various people did. So the Antikythera mechanism, not sure whether that's the correct pronunciation. This is a remarkable analog computer, which is thought to date from 2nd century BC. So they found the remnants of this mechanism under the sea in Greece. And what it appears to be is an ancient analog computer that's able to predict eclipses and other astronomical phenomena. And it does it by having a whole lot of gear ratios, and you turn a handle and somehow it predicts the motion of the sun and the moon, and perhaps other things. And of course, somebody managed to make a Lego version of it. So that's somebody being Andrew Carroll. So here's what it looks like. Turn the sound off again. Okay, I'm going to skip most of this. So yeah, so yeah, somehow you turn the handle and you get predictions about eclipses. And it's all done with gear ratios, but there's a problem in that there are only so many sizes of gears made by Lego. You can have, for instance, 1:3 ratios, 1:5 ratios, but if you want to get something like a 1:19 ratio or something like that, there isn't an obvious way to do it. Well, it turns out you can do it with a differential. So here is an example. So he has a differential, and then there is some gearing to connect one of the two side shafts to the outer shell. And then, well, you have a linear equation that tells you what's the ratio of this to this, a linear equation involving the average and whatever that gear ratio is. And using that, it turns out you can get all sorts of other gear ratios and you know, arbitrary rational ratios, really. And somehow he uses all these to predict eclipses. So a remarkable piece of work. Let me tell you about something else. So here is another sort of well-known-ish phenomenon. If you have a sequence of pendulums with their frequencies in arithmetic progression, you can do this rather cool thing where you start them all going and they start getting out of phase because they have different frequencies, and you get this sort of beautiful sine wave pattern. And then after a while, when you're sort of halfway through the cycle, you end up with, well, at various points, you end up with other interesting patterns. And as you see there are sort of 3 sets, and then a bit later you have 2 sets, so 2 sine waves going through each other like that, and so on. So I thought this was nice, but the trouble is with pendulums, they die down after a while. So wouldn't it be wonderful if you could have a sort of mechanized version of this where it keeps going forever? And I managed to make one, and here's what it looks like. So this is all powered by a motor. So I'll keep going forever. For instance, there they're all lined up. If I skip ahead, there they are in sets of 3 and so on. And I also managed to make a musical version of this. So if it had a bit, you get all sorts of interesting musical effects. So how was this done? Well, this was done with differentials. So the two end gears are powered in a fixed gear ratio. And then I have a differential that splits the difference between them, and that powers the middle one. And then I have another differential that splits the difference again, a quarter of the way along, and then another row of differentials, an eighth of the way along, and so forth. And so you get the speeds in exactly arithmetic progression. And interestingly, at first I tried to do this a different way, because again, we have this sequence of axles and we want their speeds to be in arithmetic progression. Another way to do that would be to put a differential connecting 1, 2, and 3, and then another differential connecting 2, 3, and 4, another differential connecting 3, 4, and 5 in the sequence. I tried that, and interestingly, it just doesn't work. You try to turn it and it binds up. And I don't really understand why that is. It's a bit of a mystery. And I'm running out of time, but let me show you another version of this same mystery. So here, so far as I know, no one has really come up with a good explanation of this. So here is a differential in the middle. We have the two side shafts, and then this side shaft is also geared in a particular way to the outer shell of the differential. And if I turn this side shaft, then the one on the other side turns, and turns perfectly freely. And you can work out what the ratio between the two speeds is. Again, it's just a question of solving a little linear equation here. And you would think that if you turned the other shaft, then you'd just transmit the motion the other way. But actually, if you try to turn this shaft, mysteriously, the whole mechanism locks up and you cannot turn it. So again, turn this, and the other side turns very freely. Turn this, and it locks up. And it is potentially a useful mechanism, right? If you want to do various kinds of mechanical computation, potentially useful to have something like this. And I do not really know how it works. I mean, it's something to do with, where does the torque get routed? And maybe it's something to do with the fact that in the differential you have counter rotation, because sometimes the central shaft is potentially turning the opposite way from the outer shell. Maybe something to do with that. Something to do with friction, obviously, but I don't have a good explanation. So I guess I am really out of time. I just wanted to tell you really quickly a couple of things. Just talked about. I'm really interested in mechanical computation, and let me just briefly show you some favorites. So the same person I mentioned before, Andrew Carroll, managed to make a Lego Babbage difference engine. This is absolutely wonderful. So what it does is it computes polynomials, and originally the Babbage difference engine was meant to compute polynomials for the purposes of compiling tables, right? So if you want a table of sine or log, well, you can express it as a power series, and you can truncate the power series and you get a polynomial. So this actually, it computes polynomials in decimal. And again, that's the Babbage difference engine, and here it is in Lego form. Absolutely marvelous. And then, yeah, I don't really have time to talk about it, but this is an invention of mine. This is drawing a fractal curve known as the dragon curve entirely mechanically. So there's a system of Geneva mechanisms which trigger left and right turns in the appropriate sequence, and it really does recursion. So if you just, in principle, if you just added another gear, you would get a curve twice the size, the next approximation to the fractal. And one more, which I won't be able to really talk about, but here is a device which solves the Tower of Hanoi problem, probably well known to most people, entirely mechanically. So there's no computer, it's just a mechanical device. I have to explain how it works, but that's what it does. So that's a speeded up video. Yeah, there we go. And right, so how to get started with this? So honestly, the easiest way is to simply buy a Lego set. So you're looking for the word Technic. So Technic Lego set. You can buy them directly from Lego or various other places. So for instance, this one is a very nice. This NASA rover has lots of interesting mechanisms and fairly moderately priced. So if you do that, A, you'll have some pieces to play with, and B, actually, the official Lego models have a lot of interesting build techniques in them, a lot of interesting mechanical stuff. So that's the easiest way to learn about it. Buying parts, there are remarkable third-party marketplaces for buying parts. So none of the amazing things I showed you would be possible without these. So the principal one is BrickLink, and there's also BrickOwl, which is another one. Specialist marketplaces where you can buy. First of all, you can find out about any part that there's ever been, what colors it's ever been available in, and you can buy it from hundreds of sellers around the world. And yeah, various other resources. I spend a lot of time on YouTube looking at the amazing things people have done. Internet forums. There's a Facebook group called Lego Math and Patterns, which people in this group might appreciate. There's a site called Rebrickable. Many people produce instructions for their own creations. So people like me, other people who design interesting things, actually make instructions for them, and Rebrickable is a repository for those instructions and on as well. And I've just scratched the surface. There's all sorts of amazing things you can do, which I haven't even had a chance to talk about, but I will leave it there.
Well, thank you so much, Ander. This is the time when traditionally we would hear a round of applause, but this format doesn't make that easy, but I hope I'm expressing everyone's delight at the wonderful talk. There were some questions that came up. The first one you actually just answered, which was sort of, well, mostly answered, which was sort of resources to get into things. But I guess there's a slightly different sense to it, which is resources for the sort of notion of the basic linkages, and sort of once you've got beyond building bricks, what are the sort of units you can start to use to invent your own models and mechanisms?
Yeah, so I would say, I mean, there are books, but I guess, I guess they might not be quite focused on what you want. I think the best way to do it is to buy one or more Technic sets, and those will have the gears and the pins and the connectors and all that stuff. That's what they're composed of. That's what the Technic word means. And try building the official Lego set, because that will have a lot of interesting mechanisms and will help you to get started. And then start looking on YouTube and for instance, instructions on Rebrickable and other places, these forums, to see what other people do. I think that's the probably the easiest route. There's no book of how to do Lego for mathematicians, of course. Depends what you're interested in, and you have to dig a little bit.
Then we had a question from Gabriel, which was about the hexagon and the equilateral triangle.
Yeah.
With the hexagon,
yeah.
And so are they synchronized, or is one driving the other?
One is driving the other. The triangle is driving the hexagon.
And
in principle, it could be the other way around, but it's generally better to gear down than gear up. I see there's some questions in the chat.
There's two more in the chat if you
need them. So are there plans for one to 3D print their own Lego components? Yes, good question. There are. If you look in the usual places, so for instance, on Shapeways, there is, there's, do you want to 3D print it yourself, or do you want to buy it from Shapeways? There is a person who goes by the name of Efferman, EFFERMAN, because I don't know any of these people's real names, so these online handles, but he has a ton of designs on Shapeways for things that you wish Lego made, but they don't, and especially in the direction of mechanical type things. Yeah, so it's and yeah, also just go to the usual repositories where you find your 3D prints and look, and you'll find there's a bunch of people designing them. So it's interesting. So real Lego parts are made to incredibly high tolerances. So they're very, very accurately made, and that's important because you want exactly the right clutch power. So you want pairs of pieces to fit together and stay, and then, but also you want the possibility to have, you know, pieces sliding against each other or one piece rotating in another without much play. So consequently, the way they do their manufacturing, it's very, very precise, and it kind of has to be. And as a result, 3D printed parts can work, but often they don't work quite as well, and you kind of might have to sand them down and this kind of thing. And also related to that, the clone brands, which we don't like to talk about, some of them, I mean, it used to be all of them. These days, maybe they're catching up. Don't necessarily have the same quality, right? So they produce parts that look identical, but they don't work quite as well. And of course, that's one of the reasons why the Lego company really dislikes them, because it's sort of like diluting their brand. Because if someone gets one of those parts and thinks it's Lego, that's fine news for them. Then someone asks, are all these Lego models assembled one piece at a time? Are there any ways to automate their construction? Well, that would take the fun away, wouldn't it? Yeah, I'm not aware of serious attempts to automate the actual putting together of models. Maybe there are some. Yeah. Oh yes, thank you for those links. Perfect. Yes.
All right. Well, I would like to express, I think, everybody's delight and thanks to all three of our speakers again today, and again have a virtual round of applause, which is spread out over everyone's homes. And that concludes this second seminar, and we will have a new one in another month, where I think Gabriel will be back in my seat. So thank you for letting me take over for a little bit of time. So goodbye, everyone.
And if anyone is interested in continuing conversation will occur on the Discord channel. And feel free also to check out the website that I just put in the chat, illustratingmath.org. Thanks again, Edmund, and all the speakers, and all of you for coming, and we'll see you next time.